The title of this presentation is Eigenvalue Attraction. To begin with a presentation overview, we'll be describing a 2015 reference from the Journal of Statistical Physics on Eigenvalue Attraction by Movasa, in which he provides formulas for the second time derivative of eigenvalues and draws our attention to additional prospects of applying this framework for other systems of interest in physics, which we'll be discussing. And that is, we will want to apply and make use of this framework to open quantum systems, biophysical systems, and parity-time symmetric materials. So as an introduction, this is a reference that we mentioned in the previous slide from 2015 from the Journal of Statistical Physics, in which one of the open questions or open directions of interest for future research is making use of and determining whether eigenvalue attraction framework can be applied for other systems of interest, in which the eigenvalues and eigenvectors are obtained from a real matrix, n by n real matrix, and there's an expression obtained for the second time derivative of the jth eigenvalue. And this is helpful for at least determining how different components of the formula interact, namely how there are inertial forces, and there are also forces from the remaining eigenvalues in the spectrum. So we'll want to quantify and further examine the spectrum of different physical processes within this framework. So the framework begins with the following. We'll first need to make use of a probability measure boldface P on standard normal random variables. And for an n by n real matrix M of t, which is in the space R to the n by n, which is parametrized in some time t, the force big F between the eigenvalues and its complex conjugate takes the following form. So with respect to the probability measure boldface P on standard normal random variables, we can take the expectation of the sum of J over the naturals, namely J over the positive integers, of the force that the complex conjugate of the jth eigenvalue bar lambda of J exerts on lambda of J. And from a line or two of computation, we can express this expectation of the summation of the force of the complex conjugate of the eigenvalue on the eigenvalue itself as in terms of minus I times a summation over J times the expectation of P squared, where P squared is some real parameter, as well as the square of the L2 norm of the jth eigenvector, which is normalized in 2 times the imaginary part of the jth eigenvector. So besides this expression that we included in the previous slide for the expected force of the complex conjugate of the eigenvalue on the eigenvalue itself, we'll also want to look at a way to parameterize the matrix T, further parameterize the matrix T that we introduced in the previous slide, which is dependent on time. And this is given by the fact that we can introduce a sufficiently small parameter epsilon and take the limit as epsilon tends to 0 from a sequence of matrices m epsilon of t. And we can obtain the second time derivative of the eigenvalue by following an approach that Terence Tao made use of in one of his papers that I've included in a reference to the archive preprint, in which I make use of the eigenvalue attraction framework for open quantum systems, biophysical systems, and parity-time symmetric materials. So first, to obtain the desired expression for the second time derivative of the eigenvalue, we'll need to formulate 2 eigenvalue equations, which are the 2 following equations. We'll first need to take a look at the action of the real matrix M of t on the eigenvector Vi of t. And from the definition of eigenvalues and eigenvectors, we know that this can be equivalent to the eigenvector lambda I of t multiplied by Vi of t, as well as the fact that we can also form a second eigenvalue equation from the fact that we can look at the complex complex conjugate of the ith eigenvector Ui of t multiplied by the matrix M of t, which is also equivalent to lambda I of t times U star I of t. And from these eigenvalue equations that we provided in the previous slide, after following some of the computations, a few steps of which I've recounted and provided in the second page of the archive preprint, for looking at additional applications of the eigenvalue attraction framework, we can obtain an expression for the second time derivative of the eigenvalue lambda j of t, which is composed of the following components. First of all, in the second part, we have a summation over I not equal to j, and in the reciprocal, or in the denominator of this expression, we have the difference lambda I of t minus lambda j of t, whereas in the numerator of this expression, we have two expressions which are dependent upon the first time derivative of the real matrix M of t that we introduced a couple slides ago. So we have, besides these terms, which is m dot of t appearing in these two locations for the first time derivative of the real matrix, we also have the quantities ui star of t vj of t, as well as u star j of t vi of t. And besides the terms that are included in this summation over I not equal to j, we also have another term which precedes this in the summation, in which is proportional to the second time derivative of the real matrix M of t, as well as U star j of t. So we introduce this expression and briefly draw the attention of the viewer to the method of tau, which is used to obtain the second time derivative of the eigenvalue lambda j of t, because this is going to be the formula that we're going to be looking at in fitting different terms to for various systems of interest in physics. And we're going to first spend more time in the open quantum system area, and then we'll briefly describe and carry over in we'll briefly describe and demonstrate how these results in this thought process can be carried over to obtain an expression for the second derivative of the eigenvalue lambda j of t for the two other systems, namely the biophysical systems and the parity-time symmetric materials. So under the assumptions on the real matrix that we've been talking about, the second time derivative of the eigenvalues can also be expressed as the following. So we can also, under certain assumptions, depending upon whether the matrix is circulant, we can also obtain a different type of expression in which, for the summation, we also have a term. The summation is always also taken over I not equal to j, in which we still have the term for lambda I of t minus lambda j of t. But in the denominator of the expression, we can collapse the two terms which are dependent upon the first time derivative of the real matrix C that we've been discussing into the square of the norm of a single term, where these PA and where the terms that appear in the square of the norm in the numerator of the expression is a PA term, a VJ of A term, as well as the complex conjugate of a VAK term. And then for the other term that appears, besides the summation that's taken over I not equal to j, there's also a prefactor, which is dependent, an imaginary prefactor, which is dependent upon minus I normalized in the imaginary part of the lambda j term, as well as the square of a very similar expression, what's given in the summation. So the main result that we provide in the preprint is that we're looking at the second derivative of the lambda j of t guy for open quantum systems, biophysical systems, and parity-time symmetric materials. So this is given by the fact that because we're going to first focus on the open quantum systems and demonstrate similarities between the open quantum systems and the biophysical systems and the parity-time symmetric materials, this is the expression which we're going to demonstrate holds for the second time derivative of the eigenvalues, which is a special case of the generalized formula for the second time derivative of the eigenvalues that we provided in the earlier slide. And to further ease ourselves into the open quantum system framework and place ourselves in this mindset, in this perspective, this is important because this open quantum system framework can help us think about the preparation of thermally stable or globally asymptotically stable pure states. And this is of interest for a lot of companies of interest in quantum computing, specifically Google Quantum AI, in which from the image that's given from their website on the left-hand side of the slide, you can see that this is a picture of the wires and the interface that they prepare before covering everything with a dilution refrigerator, so that they can very specifically control the behavior of the qubits by making the apparatus extremely cold. And from the 2015 reference on eigenvalue attraction, Movasa provides our attention to this following reference that we're going to make use of and discuss, which is from 2012, which is titled Stabilizing Entangled States with Quasi-Local Quantum Dynamical Semigroups. So we'll be providing some type of overview of the quantities which are used to describe globally asymptotically pure states in this 2012 reference, and what we need to make use of for obtaining the second time derivative of the eigenvalues within this eigenvalue attraction framework that we've been discussing. So we'll need to be looking at properties of gap states, where gap again stands for globally asymptotically pure states. And for these types of states, or even for thermally stable states, we'll need to introduce a Hamiltonian. And this Hamiltonian that we've been giving, that we have in the slide, can be expressed in terms of a summation over J components. And alternatively, the Hamiltonian can be expressed as a tensor product over N components. And we'll also need a MME, which stands for a master Markov equation, which is given by a time derivative of some density rho of t. And the time density is very important for quantum mechanics because it relates to the density matrix, which can be an interpretation of describing the probability of finding different particles when confined to different regions of physical space. And this time derivative of the density is given by the fact that it can be expressed as an imaginary term times a commutator of the Hamiltonian with the density, as well as a summation over k, where the terms which appear in the summation over k is given by a Lie bracket, as well as another term which is proportional to which is also proportional to the Lindblad operator, and taking the complex conjugate, or the Hermitian conjugate of the Lindblad operator with the density rho of t. So from the master Markov equations and the globally asymptotically pure states, one can formulate the eigenvalues and eigenvectors of the Hamiltonian, which we can use to directly substitute into the expression for the second time derivative of the eigenvalues, so that we can make sense of this eigenvalue attraction framework and the inertial forces, as well as different types of forces which the eigenvalues exert, either from the complex conjugate of the eigenvalue on the eigenvalue itself, as well as the force that's exerted on the remaining eigenvalues that are in the spectrum of whatever real matrix we're looking at. So this is given by the fact that, again, we recall from the previous slide, we have a Hamiltonian which can either be expressed with a tensor product decomposition or a summation over J components, and we have the master Markov equation. And specifically, the authors of the 2012 reference describe the eigenvalues of the Hamiltonian being proportional to some Hamiltonian H twiddle of S, where H twiddle can be expressed in terms of the original Hamiltonian H, as well as an imaginary factor from a summation over K from these Lindblad operators, which we had first introduced in the master Markov equation. And furthermore, from the Hamiltonian, we can also introduce another master Markov equation, which is dependent on twiddle of H, where twiddle of H is just another Hamiltonian, which we define in terms of the first Hamiltonian, which we introduced to describe the time dependence of the system, which we're looking at, where this Hamiltonian is analogous to the real matrix, which Movasa first introduced when looking at the expression for the second time derivative of the eigenvalues, which was derived by tau. And next, we can formulate expressions or terms appearing in the eigenvalue equation for the open quantum systems, in which, as we've been alluding to and mentioning, from the Hamiltonian twiddle of H, which we obtained from the first Hamiltonian, which we introduced H, we can substitute the first time derivatives of this time-dependent Hamiltonian twiddle of H into the terms of the Hamiltonian, or into the terms for the second derivative of the eigenvalue, which appear in the summation of I over J. And as well as the fact that in the reciprocal of the summation over I not equal to J, we have the difference of I not equal to J, and we have this difference. We have the condition, we stipulate the condition in the summation that I is not equal to J, so that the summation for the second derivative of the eigenvalues doesn't diverge. But besides the eigenvalues and the first time derivative of twiddle of h, we also have a bar of psi I, as well as psi j, as well as a bar of psi j and psi I, which are just given by the eigenvalues and the eigenvectors of the open quantum system, which are either given by Bra or Ket states, which live in the Hilbert space. And then besides the summation of I not equal to j, we also have the fact that there's the other term, which is given by the bra of bar of psi j, as well as the second time derivative of twiddle of h. So this is demonstrating how one can make use of and look at the eigenvalue attraction framework for open quantum systems, and how we can fit different types of terms and make interpretations of globally asymptotically pure states within the context and perspectives that we've been providing, and how this can be of use for a reliable and a scalable quantum computation. And so, as we've been alluding to, this isn't the only type of framework that we can apply the eigenvalue attraction framework to. In fact, we can look at making use of this framework and similarly applying it to other systems of interest, namely biophysical systems and parity-time symmetric materials. And the main jump, or the main conceptual jump or realization that anyone has to have when looking at making use of the eigenvalue attraction framework for these two remaining frameworks, is the fact that we have to look at some type of real matrix which describes some physical system of interest which is dependent upon time, and then fitting this in from this matrix, being able to obtain the eigenvalues and the eigenvectors. So I go into more depth about how to make use of this connection in the preprint, and it's a pretty short preprint, only at 10 pages, and you can just look at the computations which follow from the fact that for a biophysical system, the real matrix that we look at is some matrix omega, which we've given here, which is a tridiagonal, it's almost a tridiagonal matrix, with the exception that along the last entry of the first column, we have a non-zero entry D, as well as in the last entry of the first row of the matrix, we have another same non-zero entry D. As well as for the fact that parity-time or PT symmetric materials can lead us to an expression for the second time derivative of the eigenvalues from the fact that we can look at the scattering in M matrices, which are given here. So I'm not going to provide what the eigenvalues and eigenvectors are from the scattering matrix and the M matrix I've given here, but it's just a couple of lines below which demonstrate the connection between these two matrices, and how one can look at entries of these matrices to be able to also formulate the second time derivative of the eigenvalues. So the conclusions that we're going to provide to close out is that we describe the eigenvalue approach from the 2016 reference or 2015 reference Yuta Movasa, and we apply that framework to other systems of interest in physics, and it's very much demonstrating the connection between quantum physics, mathematical physics, and statistical physics, in which the expression for the second time derivative of the eigenvalue that we have is dependent upon the following three components. We first need a real matrix, and then from this matrix, we can extract the eigenvalues of the matrix and the eigenvectors of the matrix. And then we also provided expressions for the second time derivative of the eigenvalues for the open quantum systems. And we demonstrated many similarities between these different types of physical systems that a priori may not appear to share any commonalities at all. And thanks for watching.